I'm analyzing a scenario involving optics clustering, a technique used to group similar data points. Think of it like sorting Lego bricks by color and shape. I'm working with optics, a clustering algorithm in Sklearn. I've run the algorithm with specific settings, and the resulting plot shows clusters, but there's a region of points that don't clearly belong to any cluster. My goal is to understand what's happening in this high reachability distance area and how to improve the clustering result. It's like a detective puzzle. This is a visualization created by the optics algorithm. It shows how far each data point is from its neighbors. Valleys in the plot represent clusters, while high points signify regions where points are distant from each other, often noise. Think of it as a landscape. Valleys are towns and mountains are unpopulated areas. These are settings that I use to control how the optics algorithm behaves. They influence the outcome significantly. This parameter determines the minimum number of points required to form a dense cluster. Increasing it makes the algorithm less sensitive to noise and small clusters. This parameter controls the reach of a point's influence during cluster formation. A smaller xi makes the algorithm more sensitive to density changes. Think of it as the reach of a point's influence on its surrounding points when forming clusters. A high reachability distance region usually suggests noise or points that don't belong to any particular cluster. In my plot, it's a region between clear clusters. By increasing the minimum number of points needed to form a cluster, I can make the algorithm less likely to identify noise points as separate clusters. It's like raising the bar for what constitutes a cluster. Reducing xi increases the sensitivity to density changes, which can help to better separate clusters and reduce the size of the high reachability region. Think of it as making the algorithm more picky about cluster formation, resulting in tighter clusters. I don't agree. Optics handles datasets with varying densities and noise well. The problem is likely with the parameter settings, not the algorithm itself. Let's not give up on optics so easily. I'm analyzing data using optics, a clustering algorithm in Sklearn. Optics stands for ordering points to identify the clustering structure. It's great for datasets with varying densities and noise. I've run optics with {min_samples equals 5 and xi equals 0.05 . My reachability distance plot shows clusters separated by a region of high reachability distances, indicating potentially noisy data or a transition zone between true clusters. I need to understand what's happening in that high reachability area and what I can do to improve the clustering. Here are some possible explanations for the high reachability distance region. I'll evaluate each statement. This is a good possibility. High reachability distances mean points are far from their neighbors, which is a hallmark of noise. Increasing {min_samples} makes the algorithm less sensitive to small clusters, including potential noise. It'll require more points to form a cluster, effectively filtering out small, noisy groups. {xi} controls the reach of a point's influence. A smaller {xi} makes the algorithm more sensitive to density variations, possibly resulting in more clearly defined clusters and a reduction in the high reachability zone. I don't think so. Optics is designed to handle noisy data and varying densities. The problem is likely due to parameter settings, not an inherent limitation of the algorithm. I disagree with this statement. Optics is a powerful algorithm, designed to handle datasets with varying densities and noise, like the one described. The problem is likely due to the parameter settings or the data itself, not optics's limitations. It's not about the algorithm being unsuitable. It's about finding the right settings or maybe even considering another algorithm if this one is not giving good results after trying different configurations. The dataset contains points that are far from any clear clusters, noise. These points are scattered between the actual clusters, making it challenging to separate them. Think of it like trying to sort colorful candies. You have distinct piles of red and blue candies, but also a bunch of oddly colored ones scattered everywhere. Those oddly colored ones are the noise. We're using the ordering points to identify the clustering structure, optics, algorithm. {min_samples} set to 5, tells optics how many points must be close together to form a cluster. {xi} set to 0.05, controls how far optics will reach to consider points as connected. These parameters influence how optics finds and separates clusters. We're trying to group similar data points together using the optics clustering algorithm. The goal is to find meaningful clusters within the dataset, ignoring or minimizing the impact of noise. This is a multiple-choice question designed to check your understanding of optics clustering and how to interpret its results and how to tweak the parameters to improve the algorithm's behavior. We are performing cluster analysis on a dataset using the optics algorithm, focusing on the interpretation of results and the effect of algorithm parameters. The reachability distance plot shows clear valleys representing distinct clusters. The high region between these valleys is a key area of focus because it indicates the presence of noise or transition zones between clusters. It's this area we want to understand better. This question tests understanding of OPTICS's output and how to interpret its results, including the meaning of the high reachability distance region, the impact of "min underscore samples" and "she" parameters on clustering behavior. I see a dataset with two clearly defined clusters. There's a noticeable gap between them filled with points having high reachability distances. Think of it like two islands with a wide, deep ocean between them. This question tests your understanding of optics clustering and its parameter tuning. You need to choose the statements which correctly interpret the reachability distance plot and the impact of optics parameters. The wide ocean between my islands? Yep, that's a strong indication of noise, data points that don't easily fit into either cluster. Increasing "min underscore samples" means I'll need a larger group of points to form a cluster. This makes my algorithm less sensitive to small, noisy groups and will clean up the noisy data better. A smaller "she" makes the algorithm more sensitive to density changes. That means the algorithm will better distinguish between dense clusters and the sparse area between them, making the noisy region less noticeable. Think of it as refining the lens I use to see those clusters. No way. Optics is great at handling noisy data, especially with varying densities, like our islands in the ocean. The problem isn't optics itself, it's likely my parameter settings. This describes the basic setup. Two well-defined clusters, my islands, are separated by a region of points with high reachability distances, the ocean. This is a multiple-choice question that evaluates your understanding of optics. You're asked to interpret the clustering output and explain the impact of parameter changes on the algorithm's performance. It's a recap of the question which asks you to select all correct statements describing the provided scenario related to the optics clustering algorithm. Let's get to it. I'm analyzing a dataset using optics clustering in Sklearn. I've set the minimum samples parameter, "min underscore samples" to 5 and the reachability distance parameter, "she" to 0.05. My reachability distance plot shows clear clusters, but there's also a large area between the clusters with consistently high reachability distances, suggesting many points are far from their neighbors. That's correct. A large region of high reachability distances often points to noise in the data. These points don't easily fit into any cluster because they are too far from other points. I agree. By increasing "min underscore samples" I'm essentially raising the bar for what's considered a dense cluster. This means that only groups of points that are sufficiently large and close together will be considered clusters, effectively filtering out the noisy points that don't meet this stricter criteria. You got it again. The "she" parameter controls the reach of a point's influence. By lowering "she" I'm making the algorithm more sensitive to density changes. This heightened sensitivity should lead to tighter, more well-defined clusters, and reduce that noisy region between my well-defined clusters. That's incorrect. Optics is specifically designed for datasets with varying densities and noise. The problem isn't with optics itself, it's likely a matter of fine-tuning my parameters. I see a high reachability distance region in the optics plot. That means points are far from their nearest neighbors. That's a big hint there's a lot of noise or a gap between clusters. Think of it like this. Imagine searching for similar houses in a city. A high reachability distance would be like finding a house far away from any other similar houses. It is probably an outlier. Pretty cool, right? The "min underscore samples" parameter in optics controls the minimum points needed to form a dense cluster. If I increase this number, I'm making the algorithm stricter. It will be less likely to consider small groups of points as clusters, effectively filtering out noise. Think of it like raising the bar. Only larger, more significant clusters will be identified. The "she" parameter in optics affects how far a point's influence reaches when forming clusters. By reducing "she", I'm making the algorithm more sensitive to density differences. This leads to tighter clusters and smaller gaps between them, reducing the prominence of noisy regions. It's like zooming in on a map. You'll see more detail. I disagree with this statement. Optics excels at handling datasets with noise and varying densities. The problem likely stems from the parameter settings I chose, or simply from the nature of the data itself. Don't give up on optics so easily. I see a problem here about understanding how optics clustering works and how to interpret its results. We're looking at a reachability distance plot that shows clusters and a noisy region between them. This is the core question. We need to determine which statements correctly explain the meaning and implications of that high region in optics output. This statement suggests that the high reachability distance region corresponds to noise points in the dataset. I think that's a valid interpretation because these points are far from their nearest neighbors. Here we're discussing the impact of changing the "min_samples" parameter. Increasing this value means optics will need more points to form a cluster, filtering out noise and possibly leading to better cluster separation. I find this to be a reasonable approach. This statement focuses on another parameter, "she". Decreasing it increases the sensitivity of optics to density changes. I can see how this might lead to tighter, more defined clusters and a reduction in that noisy area. This statement suggests that optics is not the right tool for the job. I disagree. Optics is specifically designed for datasets with noise and varying densities, so this is incorrect. This defines "min_samples". It tells us how many points are needed to make a group be considered a dense cluster within optics.